So yesterday we started a discussion of the different types of masses that neutrinos can have, Majorana mass and Dirac mass. We discussed the seesaw mechanism. And we also discussed the direct mass measurements for the tau-neutrino, mu-neutrino, and electron-neutrino, which are all summarized on this graph. You remember this was the plot of the mass of the neutrino versus the lifetime of the neutrino, covering masses from microelectron volt to about TeV, and lifetime from a millisecond to the age of the universe. And we found out that the electron neutrino is limited by about 7 electron volt, the mu-neutrino 270 kilovolt, the tau-neutrino 31 MeV, and a possible fourth neutrino is limited by the lab measurements to be above 45 GeV. So between 30 MeV and 40 GeV, we clearly have an empty region and no neutrino masses can be found. We then moved on to the discussion of cosmological bounds on neutrino masses. And let me start by repeating very quickly what I said in the last few minutes of the first lecture. First of all, we discussed the total density of the universe, still without any relationship to neutrinos. And we said that the present energy density of the universe, rho 0, is given by omega little h squared times 11 kilovolt per cubic centimeter. The 11 kilovolt per cubic centimeter is computed from the dimension of the gravitational constant and the Hubble parameter. And the two dimensionless parameters, capital omega and little h, are representing as follows. Omega is the number which is equal to 1 for a flat universe. It is larger than 1 for a closed universe, that is for a universe that will eventually collapse upon itself, and is less than 1 for an open universe, namely a universe which will continue expanding forever. And we said that the theoretical prejudice is that omega is equal to 1, and that most of this omega equal to 1 is presumably due to invisible dark matter. Little h is the Hubble parameter measured in these units of 100 kilometers per second per megaparsec. And we know from various observations and analysis of astrophysical and cosmological facts that it has to be somewhere between 0.4 and 1. And I mentioned that there's a big dispute on the actual value of this, but we will only assume this range and will not get into this dispute. We also noted that the two numbers are related by relationship involving the age of the universe, and I told you that if the age of the universe is approximately 15 billion years and omega is equal to 1, h has to be approximately 0.4 for a universe that is dominated by matter. With all of these considerations, it seems that the energy density of the universe in a very conservative bound is definitely less than 7 kilovolt per cubic centimeter, and is probably around 2 kilovolt per cubic centimeter in the case that omega is equal to 1 and the age of the universe is 15 billion years. Now, this has nothing to do with neutrinos except for the fact that the total energy of all the neutrinos has to be less than this number, obviously, and also that if neutrinos are the cosmological dark matter, then to a good approximation, the total mass of all the neutrinos has to be approximately equal to the numbers I just gave you. And in order to learn something about the mass of the neutrino itself, we then have to know how many neutrinos there are in the universe, or how many neutrinos there are in every cubic centimeter. And that was the other thing we did towards the very last 2 minutes of the lecture, and that is the classical standard analysis with standard cosmology, Big Bang cosmology, of the number of neutrinos in the universe. Now, this analysis relates only to light neutrinos, that is, neutrinos which are lighter than an MeV, and only to stable neutrinos, neutrinos which do not decay. And I will explain the word stable in a minute in more detail. Light neutrinos, because we are talking about neutrinos that were relatively massless or very light at the time of decoupling. The time of decoupling in the history of the universe was when the temperature of the universe was approximately 1 or a few MeV. This is approximately 1 second after the Big Bang. And after that time, the density of neutrinos in the universe is such that the probability of neutrino interactions is negligible, and neutrinos can be treated basically as a free, non-interacting gas. And the number of neutrinos that existed at that time is basically the same number of neutrinos that we have today in the universe, except the density is, of course, getting smaller all the time because of the expansion. And the number of neutrinos is proportional to the number of photons by this parameter 3/11, which is obtained by counting degrees of freedom and is not a very profound parameter. And since we know from the microwave blackbody radiation that has been observed experimentally, the famous 3 degrees background radiation, that in every cubic centimeter in the universe today there are about 400 photons, it follows that the number of neutrinos in every cubic centimeter is 3/11 times 400, which is 110 neutrinos of every kind, electron neutrino, mu-neutrino, tau-neutrino per cubic centimeter. And if there's 110 such neutrino in every cubic centimeter, and the total energy density of the universe is less than 7 kilovolt per cubic centimeter, it follows that the mass of each neutrino has to be less than 65 electron volt. And if we take the favorite value of omega equal 1 and 15 billion years, the mass of the neutrino has to be less than about 20 electron volt or so. And furthermore, if one of the neutrinos is the cosmological dark matter and does account for almost all the matter of the universe, namely if omega equal to 1 or omega equal to 0.9 is due to one type of neutrino, the mass of that neutrino has to be approximately 20 electron volt, perhaps 15, perhaps 25. There is some uncertainty, but it is that order of magnitude. Now, of course, we do not know if the neutrino is the dark matter, but it therefore means that neutrinos has to be at this range of electron volts or less, but only if they are light stable neutrinos, namely, if they are below an MeV, they have to be below about 20 electron volt. So they cannot be between an MeV and 20 electron volt. And even that is true only if they are stable. We will come to the case of unstable neutrinos in a minute. Now, there's another case which used to be a very interesting case, and it's still theoretically interesting, but it's practically totally useless now. And that is the case of a heavy stable neutrino, namely neutrinos which are stable but are heavier than 1 MeV, and therefore at the time of decoupling they were not of negligible mass relative to the temperature of the universe. There's a very interesting argument which I do not have time to discuss, which is due to this gentleman in the 1970s, and that argument shows that in that case, the heavier the neutrino is, the lower is the number density of such neutrino, and it actually falls exponentially or like a large power. And when you complete the calculation, you find that such heavy neutrinos which are above 1 MeV have actually to be above 4 GeV, and they cannot be between an MeV and a 4 GeV. So this is a very exciting and interesting result about stable neutrinos. It says that if the neutrino is below an MeV, it has to be below 20 or 60 electron volt. And if the neutrino is above an MeV, it has to be above 4 GeV. And it cannot be anywhere between these two lines. This is for a stable neutrino. The reason why this bound now is completely useless is because we know that anyway the 3 known neutrinos are below 4 GeV, and the possible fourth neutrino is already limited by LEP to be above 45 GeV, and therefore knowing that any possible additional neutrino is above 4 GeV is useless information because it is a bound less important than the LEP bound. And therefore this beautiful argument, which is theoretically beautiful, is completely useless for the time being. And that brings me to the issue of unstable neutrinos, because I repeated several times saying that the limit of 20 or 60 electron volt is for stable neutrinos. Now, first of all, what does unstable mean? And second, what changes in the argument if the neutrino is unstable? Unstable, of course, means a neutrino which can decay, but for all practical purposes, if the lifetime of the neutrino is substantially larger than the age of the universe, although it decays, it can be considered stable for this purpose. Because if all the neutrinos that existed at the time of decoupling, after 1 second of the life of the universe, have not yet decayed, then they are practically stable for the purpose of our analysis. It doesn't matter that they will decay eventually with a lifetime of, let's say, 10 to the 30 seconds or something like this, if the present age of the universe is only 10 to the 17 seconds. So stable really means stable with lifetime substantially larger than the age of the universe, because this is a practical issue here. On the other hand, it is absolutely clear that in principle, neutrinos are unstable. As we will see in about 5 or 10 minutes, the tau-neutrino, if it is heavier than the mu-neutrino, must decay to the mu-neutrino, and the mu-neutrino, if it is heavier than the electron-neutrino, must decay to the electron-neutrino. So neutrinos, at least 2 of the 3 neutrinos will decay to the lower neutrino. And how much and how fast and in what decay modes we will discuss a little later. So I would like to make this very clear. On one hand, it is essentially clear that if neutrinos have masses, 2 of the 3 neutrinos are unstable. On the other hand, for the cosmological argument, what matters is not whether it's stable or unstable, but whether it lives longer than the present age of the universe or less than that. And that's an entirely different issue. I would like already to anticipate the final answer that I will try to give you. I will try to convince you that it is very likely, it cannot be proven, but it is very likely that the neutrinos decay, but their lifetimes are much larger than the age of the universe, and therefore, for practical purposes, they are stable. But in order to reach this conclusion, we have to go through a complicated analysis, both of the cosmology side and the particle physics side, and also insert a little bit of astrophysics into it. Why is the case of unstable neutrinos different? Because imagine a situation in which the lifetime of the neutrino is very short. Then neutrinos decay quickly, and their mass converts to radiation, essentially to kinetic energy of the decay products, let's say the lighter neutrinos. And then for a certain period, the universe then becomes not mass-dominated, but radiation-dominated. And a universe which is radiation-dominated does not behave exactly in the same way as a mass-dominated or matter-dominated universe. It behaves in a different way, and in particular, the density of the universe relates to the expansion parameter not as an inverse Q, but as an inverse 4th power. Now again, I don't have time to get into the entire discussion, but it is clear that the situation then changes in that case, and that the earlier the neutrino decays, the more freedom we will have to populate the universe with higher masses. And therefore, qualitatively speaking, and I'm not deriving here anything, it is clear that for a neutrino that has a very, very short lifetime, there will be practically no limitation on masses. On the other hand, for a neutrino that has a very long lifetime, for instance, the age of the universe, it will behave like a stable neutrino, and there will be a severe limit on the mass, which we already derived in the case of stable neutrino. And in between, there will be intermediate values of the masses. And when you go through the careful analysis, you again find 2 cases. The case of light neutrinos, neutrinos below MeV, and the case of heavy neutrino above MeV. And when you go through the analysis, which is, again, 15-year-old and was done mostly by the people whose names were mentioned on the previous transparencies, you find that for light neutrinos, you have a bound, which is the mass square of the neutrino times the lifetime has to be less than a certain number. Never mind what the number is. I will show it to you on the graph, and it will be much more meaningful. And for the case of the heavy neutrino, this combination, namely the inverse fourth power times the lifetime, has to be less than a certain different number. Now, all of this looks very confusing, but it can be summarized in a very neat way on one graph, and suddenly it will all become very clear. Let us return again to the plot of mass versus lifetime. And now I can add on it the full information that we have from cosmology on the neutrino masses. And let's just look at it carefully and try to understand it. First of all, the MEV range is the decoupling mass, and there are two cases, the case of light neutrinos below MEV and heavy neutrinos above MEV. Below MEV, if it is stable, it has to be below this range. This is the range of 20 to 60 electron volt. If the neutrino is the dark matter, neutrino dark matter, then it has to be exactly here. And if it is not the dark matter of the universe and it is stable, it has to be below this. Or, if the neutrino is heavy, it has to be above 4 GeV, which we already declared to be an interesting but a useless bound because the left bound is stronger. Now, for the neutrinos which have decays, neutrinos which have short lifetimes, we have a limit of m squared tau for the light neutrino case and a limit of m to the minus 4 tau for the heavy neutrino case. And because this is a log-log plot, here you have the log of the mass and the log of the lifetime, any of these things is, of course, a straight line on such a plot. And the neutrinos can only be to the left of the red line. Please ignore this dotted area for 1 minute. Now, that means that a neutrino with a lifetime, let's say, of 1,000 seconds, which is about a quarter of an hour, that type of a neutrino could have any mass. There's absolutely no cosmological limitation. On the other hand, a neutrino with a lifetime, let's say, of 1,000 years, which is somewhere here, could only be lighter than something like, whatever it is, 50 kilovolt, or it can be heavier than maybe 100 MeV, but that is useless because all the neutrinos are known from the direct measurements to be below 31 MeV. So you see, anyway, we are interested only in this range, because all three neutrinos are below 31 MeV. And therefore, if the lifetime of the neutrino, let's say, is 1,000 years, it has to be below this range. And if it is, let's say, here, it has to be below this, etc. So we have eliminated only this area of the plot. But it means that if neutrinos have to be heavier than 60 or 50 or 20 electron volt, they have to decay, and they have to decay fast enough. Fast enough means that they are to the left of this in the plot. So that is the summary of the cosmological situation, and in a minute we will return to it from the point of view of particle physics. But before we do that, we want to spend... oh, incidentally, I still owe you an explanation of this dotted area. The cosmological limits are the solid line here and here. But there is an analysis performed by Steigman and Turner, and there is also analysis by some other authors, showing that if you want the neutrinos to participate in the creation of large-scale structure in the universe, because remember that one of the most profound and most fundamental unsolved problems of cosmology is how the galaxies and the clusters of galaxies and all the complicated large-scale structures of the universe have been formed, and that requires a certain ability to clump, to create large chunks of matter. And by looking into that, they found that this cosmological limit can actually be even improved by a little bit and moved here to the left by about that amount. So that area here is your ability to improve the cosmological limit, but by arguments which depend on things which are much more suspicious and much more dubious than just standard Big Bang cosmology, namely detailed analysis of large-scale structure. I'll come back to this in a second. But before we now discuss neutrino decays, we have to say a few words about dark matter. Now, This is only one simple transparency. There is no attempt here to discuss the issue. The issue can be the subject of a series of lectures by itself, but there are a few points I would like to make. First of all, for the purpose of these lectures, I will discuss only the cosmological dark matter, namely the dark matter that fills the entire universe and is presumably responsible for omega being equal to 1 or omega being large, let's say 1/2 or 3/4 or whatever it is. But we are not talking for the purpose of this lecture, but we remember that there is also other types of dark matter, because there are also missing dark matter in galaxies and in galaxy clusters, etc. And it is not absolutely clear that the dark matter missing in galaxies is the same as the cosmological dark matter. Now, I'm not passing judgment whether it is the same or it is not the same. I'm only saying that the information that we are using for the purpose of this analysis is only the information from the cosmological dark matter, from omega being equal to 1 or being of order 1, and we are not discussing the other thing. It is possible that the missing dark matter in galaxies is of a more mundane nature, and the cosmological missing dark matter is neutrinos. It is also possible that all of them are the same type and none of them is neutrinos, etc. The standard candidate for the cosmological dark matters are, number 1, possible a light neutrino, in which case it must have a mass of the order of 20 electron volts. Number 2, a weakly interacting massive particle, in particular supersymmetric particles, neutral, invisible, elusive supersymmetric particles, who could have masses of the order of a few GeV and could account for the dark matter of the universe. This is what is known as cold dark matter. A third possibility, which recently has been a little bit out of fashion, but I don't think can be completely excluded, is the possibility that dark matter is axions, the so-called invisible axions, which couple very, very weakly to fermions. In fact, they couple with a coupling constant with the Yukawa coupling, which is inversely proportional to some new physics scale, and that new physics scale has to be, because of all kinds of arguments, of the order of 10 to the 12 GeV, although even that begins to be closed by various arguments. I don't want to get into it. And then there are all kinds of other exotic possibilities, including the most uninteresting possibility that this is some dark baryonic matter of some ugly form, which nobody understands at the moment. Of all of these things, needless to say, the only one that surely exists, not necessarily as dark matter, but as a particle, is the neutrino. The others may or may not exist. So for every one of these candidates, there are several questions. The first question is, do they exist? And the answer is yes for the neutrino and maybe for the rest. The second question is, can they clump? Can they create all the large-scale structure? And the answer to this cannot be given by yes or no. There are hundreds, if not more, theoretical papers on the subject with complicated computer codes. Some versions demand a combination of hot and cold dark matter. Some favor cold dark matter. There's all kinds of schools of thoughts on the subject, and I have no wisdom to add except that this is a science which is really in its beginning, in my opinion, in spite of the fact that lots of good people are working on it for a long time. And the third question, is there only one kind of dark matter? There could be several kinds of dark matter, one in galaxies and one in the cosmos in general. But even the cosmological dark matter could in principle be of two components. It's not excluded. It would be somewhat ugly and disappointing, but it's not excluded. So there are a lot of possibilities. On the other hand, if we find a neutrino which has a mass of 20 electron volts, then there may still be other particles in the world, but that neutrino alone will provide us with the cosmological dark matter of the universe, regardless of what various people say or write about clumping or non-clumping. It will then be their problem to understand how the galaxies were formed, because if there is such a neutrino, it is then unavoidable that it gives you the full energy density of the universe. That is why the neutrino mass is such an important issue in connection with cosmology and with dark matter. But having said this, we have to return to our picture, which at the moment looks like it is still wide open and neutrinos could still be anywhere here at MeV, KeV, and we would like now to discuss particle physics and neutrino decays to see how fast the neutrino can decay. And here is a list of possible neutrino decays. In fact, not possible neutrino decays, but neutrino decays which absolutely should exist. Number one, a neutrino should decay at neutrino plus gamma. A neutrino can also decay to a lighter neutrino and 2 gammas, or 3 or 4. A neutrino can decay to 3 lighter neutrinos. For instance, nu mu could decay to nu e, and nu e bar. A neutrino which is heavier than 1 MeV, and that could only be the tau-neutrino, could decay to a lighter neutrino plus an electron-positron pair, because electron-positron pair is about 1 MeV. And finally, a neutrino could decay to a lighter neutrino plus a Goldstone particle, for instance, a majoron, which is a hypothetical, massless, weakly interacting Goldstone particle, which is coupled to the violation of lepton number conservation. We don't know that such a particle exists, but if it exists, there could be such a decay. Let us first of all see what kind of mechanisms could lead to such decays within the framework of the standard model. Now, I have to explain what I mean by standard model. In the standard model, the neutrino really doesn't have a mass, and therefore it doesn't decay. But what I mean is take the standard model and give the neutrino a mass by hand, but don't add any new interaction, don't add any new symmetry, don't add anything. Just give the mass by hand and see what happens. And then you immediately see, for instance, that the mu-neutrino can decay to electron neutrino through such a diagram, which has a loop with a W here and with a muon and an electron here. The W emits a photon. The contribution of this diagram can be calculated. It is not zero. The decay will definitely proceed. And there's no question about it that the tau-neutrino can decay and the mu-neutrino can decay in this way. How fast is another question, but they can decay. They also can decay with the emission of 2 photons, and that is non-trivial. You would think 2 photons will be factor alpha, order alpha, below 1 photon, but it's not true because there's a kind of a G mechanism which is suppressing this, and there is no G mechanism which suppresses here. So here you are suppressed by G mechanism and 1 power of alpha, and here 2 powers of alpha, so the 2 decays are more or less, could be more or less comparable. A third thing that can happen is even more surprising. A neutrino could decay to 3 neutrinos by Z exchange. And here you have flavor changing of neutrinos, let's say nu tau to nu mu, exchanging a Z. Now you know very well that this diagram is forbidden for flavor changing quark. You cannot have, for instance, a charm quark become a U quark to lowest order by exchanging a Z. But that is because the mixing matrix of the quark is a unitary matrix, and you can always choose a basis in which the quark here is diagonal, and in that basis it is trivial to show that you cannot exchange a Z. In the case of the neutrinos, life is more complicated because you've seen yesterday in the lecture that the mixing matrix of the neutrino is not a 3 by 3 matrix, but is a 6 by 6 matrix. It is 6 by 6 because we have 3 light neutrinos and 3 heavy neutrinos because of the Majorana mass. 3 light neutrinos are the physical neutrinos that we see and love, and 3 heavy neutrinos are very, very heavy, and we've never seen them. But therefore, the mixing matrix of the 3 by 3 neutrinos, which we know is not exactly unitary, it is almost unitary, it is a little bit away from being a unitary matrix, and that allows a very small but non-zero coupling for the Z boson from one neutrino to another. So you can have a small tau-neutrino Z mu-neutrino coupling, and such a coupling allows such a decay, and it can be calculated. And finally, this is trivial. Neutrino can always emit a W, become an electron, and then the W electron becomes an electron and neutrino. So all of this can happen, and therefore it is absolutely clear that the neutrinos will decay. The only question is how fast they will decay, but it is absolutely clear that they will decay. When you analyze the decay rates of all of these things, And I will not present a detailed analysis. This was all done 10 or more years ago by various people. When you analyze the decay rates of these particular decays, you find that they are hopelessly slow. In other words, when you go back to this graph here, you find that all of these decays that I listed are way out here to the left in terms of the lifetime. And therefore, you find yourself with a conflict which says, cosmology tells you that neutrinos can have a mass of this order of magnitude only if they have a lifetime below this value, and particle physics says that all these straightforward decay modes that I listed will have lifetimes much higher than that. So as far as the standard model is concerned, all these simple decays of emitting a gamma ray or two gamma rays will never give you a lifetime which is short enough or a decay which is fast enough to conform with the cosmological rules. And if this would be the only decay modes that we have to worry about, if this would be the only decay mechanism that we have to worry about, then we would find that neutrinos cannot have masses above 20 or 50 electron volt, because cosmology says that if they are heavier, they have to have a lifetime below a certain value, and particle physics says that yes, they will decay, yes, they are unstable, but the lifetime is much above the same value, and therefore between the cosmology on one hand and the particle physics on the other hand, you can eliminate all this area, and you remain with the situation that the neutrino is practically stable and has to be below 20 or 60 electron volt. But that is not the end of the story, because we said that in the standard model the neutrino doesn't have a mass anyway, and when it does have a mass, as we've seen yesterday through the seesaw mechanism, it must come from some new physics. And the new physics can be grand unification, it can be some horizontal symmetry, it could be some right-handed W bosons, which are heavier, it could be some substructures of all the quarks and the leptons, could be anything. And all of these things could also give mechanisms which would allow such processes to exist. So here are some diagrams that would happen in models which are beyond the standard model. For the case of a decay with one photon or two photons, you have essentially the same thing, except you will have in the loop particles which are much heavier, and therefore the decay rates will be even slower. And in particular, if the new physics is of the Planck scale or grand unification or even something like 10 to the 11 or 10 to the 12 GeV, there will always be propagators of that order of magnitude here, and that will only slow the decay mode, and the matrix elements will be even smaller, and therefore the lifetime even longer. The only dangerous places are two. One is the possibility for the decay of a neutrino to three neutrinos. This is a highly invisible decay, not even a photon anywhere, not by the exchange of a Z, but by the exchange of all kinds of other bosons. Such other bosons could exist in many, many theories. If there is such a thing as a horizontal gauge boson connecting different generations of quarks and leptons, it could transmit such a decay. If there are right-handed Ws, if there are additional Higgs particles, if there are triplet Higgs particles, all kinds of things like this could communicate such a transition. Similarly, you could have such things for this kind of neutrino. And last but not least, you could have a neutrino emitting one of these myons and becoming actually an anti-neutrino, because the myon carries with it 2 units of lepton number, so it converts a neutrino to an anti-neutrino. So the two really dangerous things are these types of decays and these types of decays, and both of them could be much faster than all the other decays, and they are the dangerous one, and if the neutrino is to survive as a relatively heavy neutrino, this is the only way it can happen. So let us spend a couple of minutes on each one of these cases. First of all, this case. This case is actually great fun, because if you go through all kinds of models, no matter how crazy, and you don't have to believe in them, that could transmit the decay of neutrino to three neutrinos, you find something very interesting. Here are 3 examples of such models. And again, you don't have to believe in them. One is a left-right symmetric theory in which the gauge theory of the world is not SU2 cos U1, but is SU2 left cos SU2 right cos U1. This is not excluded by anything. In which case, there is a certain Higgs particle which could transmit this decay. The second is a possibility that there is a horizontal gauge boson which does the same. And the third is the vague possibility that all quarks and leptons, including neutrinos, have some substructure. They are composite of more fundamental objects. And then there will be some effective 4-fermion interaction which will transmit the decay of a neutrino to 3 neutrinos. Now, we have absolutely no information about the strength of the decay in any one of these 3 cases. We don't know the mass of the propagator. We don't know the effective vertex. We don't know the coupling constant. We don't know anything. But in all of these cases, we do know that exactly the same interaction would work for the case of charged leptons. Exactly the same particle or effective interaction would exist because of symmetry principle for the decay of, let's say, a mu minus, let's say, to an E plus, E minus, E minus. A muon decaying into 3 electrons. Or a tau decaying into 3 muons. Or a tau decaying to mu and 2 electrons. All the possible decays of a charged lepton into 3 lighter charged leptons. And again, we don't have time to go through the details, but you can analyze this, and you find that for every such diagram, there is such a diagram, and the couplings should be the same, the propagator should be the same, or more or less the same by symmetry considerations. And the only difference between the two is simply the masses of the participating particle, which are giving you a kinematic factor of mass to the 5th power, which is the standard factor you have whenever you have such 4 Fermi interaction. So to make a long story short, what you find in all of these cases, regardless of the numbers that you do not know, that the width for a neutrino of any kind to decay to 3 lighter neutrino of the I type decaying to neutrino J, K, and L, and each one of them could be a neutrino or an antineutrino, is related to the width of a charged lepton to decay to 3 lighter charged leptons, and here are all these examples, mu to 3e, tau to 3e, etc. And the ratio is simply the mass of the decaying neutrino divided by the mass of the decaying lepton to the 5th power, where we always assume that the decay products are much lighter than the mother particle. We are assuming here correctly that muons and electrons are much lighter than tau, and that electrons are much lighter than mu. And we are also assuming that whatever neutrinos come out, they are lighter than the mother neutrino, which is here. Now, this is very interesting, because the mass of the decaying lepton is known. We know the mass of the tau, the mu, and the e. The widths for these processes are not known because nobody has ever seen such processes, but there are very strong experimental limits on all of these processes. So this number is bound, and this number is known. And therefore, we receive a bound on what? On m neutrino to the 5th, divided by the width of this process. 1 over the width is the lifetime, so we receive a bound of the form m neutrino to the 5th times tau neutrino has to be bound by a certain number. And that bound is essentially independent of any crazy theory that you could put here, unless you could invent a theory which would allow this decay without allowing this decay, and I'm not aware of such an example. When you do this analysis, you find something which is very, very nice. And it really shows you the beautiful interplay between cosmology and particle physics. And there is a sequel to this. You find that the mu-neutrino lifetime must be very long, no matter what happens. And for the tau-neutrino, you find this limitation. And this is really cute. You find that the tau-neutrino has to be below 31 MeV from... Now, wait, we have to be very precise here. This is not something that I could allow to miss by even 1 millimeter. We know that the tau-neutrino has to be below 31 MeV. We know from the cosmology that it has to be to the left of this red curve. And now we find from this particle physics argument that I just went through that it has to be larger than this equality. M to the 5th times tau, which is this blue line, has to be above this. So you find yourself in a situation that the only place that the tau-neutrino could be is here. This doesn't write, sorry. Anyway, it is in this triangle here. That's the only place where it could be, and it is limited below by a lifetime of maybe 1 minute or so. It is limited above by a lifetime of about 1 year, and it has to be between about 1 MeV and 30 MeV. So a tau-neutrino is either in this little window between 1 and 30 MeV and between 1 minute and 1 year, or it has to be below here at the dark matter level or below. Now that's a beautiful demonstration of the power of combining the particle physics and the cosmology, and if any of these limits is improving, this will close that window. But there's another argument which already closes this window, which comes from yet another different piece of physics. And that is an argument of Kolb et al., which says the following. You remember that we said yesterday that from primordial nucleosynthesis, we have a bound on the number of neutrinos. Not only LEP told us that there are no more than 3 neutrinos, but even before LEP started, we had a theoretical bound by analyzing the helium abundance and the abundance of other light elements in the cosmos. And from the observed abundance of these elements, we can deduce that the number of neutrinos is less than 3 point something, which means that there is no fourth neutrino. I mentioned this yesterday, and I also mentioned that that bound again relates to light neutrinos, neutrinos which are much lighter than an MeV. It turns out that if you consider neutrinos of the order of MeV or 10 MeV, and this is the analysis of Kolb, they enter into that same calculation of primordial nucleosynthesis in a very complicated way. You cannot solve the problem analytically. You have to put this into a set of differential equations which have to be solved numerically with computer work. But you find that a tau-neutrino with a mass of the order MeV does not count as one neutrino for the purpose of neutrino counting for the analysis of primordial nucleosynthesis, but it counts as more than that. Under certain circumstances, it actually counts like 100 neutrinos. And under other circumstances, it counts like a few neutrinos, etc. And when Kolb and company have done the analysis, they found that for neutrinos which have lifetime of more than 1 second, they can exclude the range between half an MeV and 25 MeV. And for neutrinos with a lifetime of more than 1,000 seconds, they can exclude a slightly larger range between half an MeV and 32 MeV. They're excluding precisely the region, the last region that remained open, by combining the cosmology and the particle physics argument. It is precisely the region between half an MeV, which is here, and 30 MeV, which is here, precisely that region which can be excluded by this argument. Now, here I have to add a word of caution. On one hand, if we believe all of this, the cosmological argument, the particle physics argument, and the primordial nucleosynthesis argument, we can close this window and we reach the conclusion that tau-neutrinos must be here. On the other hand, closing this window came from 3 different directions, and there could be problems with one of these arguments. In particular, the particle physics argument is not 100% solid because somebody could invent tomorrow a model in which neutrinos can decay and charged electrons cannot decay. And also, the primordial nucleosynthesis analysis is a numerical analysis, and you always have an uneasy feeling about such a thing. But it really looks like you're down here. Now, there's one last type of decay which you have to take into the account, and it is troublesome, but we have to consider it, and that is the decay of a neutrino to a lighter neutrino plus a majoron. Now, I repeat, a majoron is, in a sense, even more invisible than a neutrino. It is exactly massless. It is a Goldstone particle. It is a Goldstone particle related to the spontaneous symmetry breaking of a global symmetry. There's conservation of lepton number. And such a decay could occur. And in a normal model which has 3 light neutrinos and 3 heavy neutrinos, you obtain the following formula, that the 4th power this time, it is not the 5th power of the neutrino which decays, this is the mother neutrino, times the lifetime, is given by this number, times 3 unknown quantities. One of them is the Yukawa coupling of this number, which is just crudely guessed to be 0.1, and therefore it enters like 0.1 divided by this unknown number square. The second thing, it depends linearly on the mass of the daughter particle, the daughter neutrino, which is here normalized to 65 eV, which is the cosmological limit. And it depends very sensitively on the mass scale of the symmetry breaking of this Goldstone particle, which in the seesaw mechanism is the same mass scale which contributes the mass of the right-handed neutrino. And that mass scale, you remember, could be the gun unification scale, it could be all kinds of things, but it's surely above 1 TeV, you would think. So again, we normalize it here to 1 TeV. Now, if you put here 1 TeV and you put here any sensible number, you again find that the lifetime of such process is too long and the process cannot proceed. There's only one exception. That is a crazy suggestion of Glashow several years ago, who said, well, I don't think that this has to be TeV or more. There can be new physics as low as 50 GeV with these myons, because if there was, nobody would have seen it experimentally. It would be very ugly new physics, because the only effect that it would have on the world is the existence of such a myon, and it would be invisible, but this cannot be excluded. And if you have here 50 GeV, then you have here a factor of 50 GeV over 1 TeV, that's 1 over 20 to the 4th power, and that changes this number and reduces it, and then you can squeeze in a certain mass of a neutrino. In that case, you have the same picture that we are now used to, but you have a line, this time m to the 4th times tau, and this line now allows you, for the tau neutrino, a very, very tiny window, just here. You see, this is, sorry, for the mu-neutrino. This is the upper limit of the mu-neutrino mass. This is the red is the cosmological limit, and the orange is this limit. And there's a tiny little place here. If the mu-neutrino is just at the upper limit, this could be allowed. And for the tau neutrino, you still have a bigger window, which, however, is again excluded by the nucleosynthesis argument of Kolb et al. And that is basically the end of the story. In other words, the summary of all of this analysis is, number one, cosmology alone cannot rule out masses. Particle physics alone cannot rule them out. The combination of cosmology and particle physics, and if you allow nucleosynthesis to add to you, can really rule out in a sensible way all the possibilities and put the masses of the neutrinos below that level. If you insist that you want heavier neutrinos, they have to be very near the limit. If you insist on having a tau neutrino which is heavier, it has to be very close to the 30 MeV, and the mu neutrino has to be very close to the 270 keV, and that is your only way out. It is unlikely. It is basically ruled out by complicated arguments which I showed you, but I will not give you a bank guarantee against it. So in all possibility, it is very reasonable that that is not the case. It is unlikely, but it would be nice to completely rule it out, and to completely rule it out requires certain experiments which we will discuss tomorrow. So that is the end of the discussion of the cosmology and the particle physics decays. You have this interesting coalition between the two, which tells you at the end, what is the summary? Neutrinos will decay, but the decays are going to be slow. Therefore, the lifetimes are going to be here, and that is ruled out by the cosmology, and therefore the end result is that probably the neutrinos, all of them, all three of them, have masses below this level, and the lifetime are probably going to be somewhere out here. much, much longer than the age of the universe, but there will be lifetimes, and there will be decay, and one day maybe we can even detect some of them. But long lifetimes, slow decays, and masses below this, unless you have this very unlikely exception. Now, all of this is very nice, but it is at the same time very disappointing, because it means that we worked so hard, and what we succeeded in doing is eliminating about 6 orders of magnitude from the map, and we also tell the nice people who do these very difficult direct measurements that they are 6 orders of magnitude away from where the action is. So how can you worry about neutrinos which are below this? Well, there's only one way, and that is neutrino oscillations. And I would like now to set the stage for a discussion of neutrino oscillations, but we will get into it in detail only tomorrow. Neutrino oscillations follow from neutrino mixing, namely from the mixing of the 3 generations of neutrinos, from the fact that on one hand you have nu e, nu mu, nu tau, which are the partners of the electron, the muon, and the tau, and on the other hand you will have 3 physical eigenstates, nu1, nu2, nu3, which are the physical neutrinos, and it is not necessary that the physical neutrinos are exactly the partners of E, mu, and tau. Let me remind you what happens in the case of the quarks, which is familiar, and this would be a good background to start. In the case of the quark, we have the charged weak current, which connects the up charm and top to down, strange, and bottom. In the first approximation, the W plus, or the charged weak current, connects the up to the down, the charm to the strange, the top to the bottom. And if this would be the only thing, then there would be a unit matrix here, and that would be the end of it. But then also, for instance, strange particles and charm particles, and no, charm particles would decay, but strange particles wouldn't decay, and bottom particles would not decay. The only decays would be up to down, charm to strange, and top to bottom. But we know that that is not the case. We know that there are decays, for instance, of strange to down. This is how a K-meson decay. And that is because there are non-vanishing matrix elements here, which means that the physical quarks are not the same ones which are the SU2 partners of the other quarks. And the matrix that gives the relation is the famous Cabibbo 2x2 matrix for 2 generation, which was generalized by Kobayashi-Moscova to a 3x3 matrix. This is the famous CKA matrix. And we now more or less know most of the values approximately in this matrix. VUS is the first angle, sine theta 1, 2. It is 0.22, and the angle is 13 degrees. VCB is the second angle, 2, 3. It is about 0.05, and the angle is about 2.5 degrees. And VUB is the third angle, theta 1, 3, the angle mixing the first and the third generation. It is, roughly speaking, on the basis of the latest Cornell results, 0.004, which is like 0.2 degrees. These are all small angles. Even the largest of them is fairly small. And that gives us a fair idea about what's happening here. Now, one more remark. In the standard model, the masses and the mixing angles are fundamental parameters unrelated to each other. And if the standard model is the end of physics, then these are fundamental parameters declared by nature or by God or by somebody, and they are as sacred as alpha and all the other fundamental constants of nature. On the other hand, we don't like to accept this because there are too many of them. There are about 17 such parameters, even if the neutrinos do not have masses. And we always hope that perhaps these mixing angles are related to the masses. And for instance, one very popular relationship that was derived in many different ways from many models says that a good old Cabibbo angle, sine theta 1, 2, is related to the square root of m down over m strange, and experimentally this is more or less correct. Similar relationships were derived for the other angles, but they are not correct experimentally, and there are hundreds of papers written about this subject without too much convincing success. But it is still, and now I'm speaking for my own belief, it is still very, very attractive to suppose that one day we will be able to compute the angles as functions of the masses. There seems to be some logic in the fact that the angle mixing distant generation is smaller than the angle mixing nearby generation. This is always the case in atomic physics, in nuclear physics, in any kind of physics. Distant levels tend to mix less than nearby level. The amount of mixing between energy levels is always somehow inversely proportional to the distance between the level. It is very attractive to hope that if you have a ratio of two quarks, mi over mj, approaching 0, that the mixing angle of the same two quarks will also approach 0. If you could play God and change the masses, that the mixing angle would change. This is all prejudice. You cannot prove here anything, but this is the kind of thing you would like to hope. Now, this is a completely open question, and I wish there would be much more theoretical attention to this question, but I certainly don't know how to attack it, and this is a basically 20-year-old question, if not more. The Cabibbo angle is this year. In fact, the Cabibbo angle, now that I think of it, this month is 30-year-old, and it's time that somebody understands it. But this is about quarks. In the case of neutrinos, the situation is more complicated. First of all, we don't know the masses in the first place. Second, we have 3 neutrinos, physical neutrinos, nu1, nu2, nu3, and the charge weak current in general is given again by a 3×3 matrix connecting these neutrinos to E mu tau. And if the neutrinos would be exactly nu e, nu mu, nu tau, then this would again be a unit matrix. But there need not be, and there should be mixing exactly like in the quark case, except here it is even worse because this matrix is not exactly a unitary 3×3 matrix because of what I said already once today and once yesterday, that this is a 3×3 matrix which is part of a larger unitary 6×6 matrix. There's a little bit of leakage from this matrix to the right-handed neutrinos. We have no knowledge of the masses, and we have no knowledge of the 3 leptonic angles. And just for the fun of it, to conclude today's lecture, if the same type of exercise for the Cabibbo angle that was the square root of md over ms would be true for the electron and the muon, then the first mixing angle for E mu theta would be the square root of me over mu. Me over mu is 1 over 200. The square root of that is 1 over 14, which is 0.07. So the first guess, if you wake me in the middle of the night and say, guess what is the value of the leptonic theta 1, 2, my guess would be 0.7. But this is pure numerology. Don't believe it for 1 minute. It just gives you an example of what you can get. The only benefit of this example is the following. The ratios of E mu tau are not completely different than the ratio of DSB or up charm top. In all of these cases, the ratio between the masses of adjacent generations are anywhere between 20 and 200. Every quark and every lepton is about 20 to 200 times heavier than its predecessor along the same line. And therefore, if the angles are vaguely related to mass ratios, then the general order of magnitude of the angles should be more or less the same for the leptons and for the quarks, because the mass ratios are more or less the same. This is a very crude argument. It could be wrong, but it is just to give you some kind of an idea. So here we are with neutrinos, which have 3 unknown masses, 3 unknown angles, and masses which are 6 orders of magnitude below any direct measurements. We've used cosmology to get rid of 6 orders of magnitude. We are now down to the level of electron volts or below. The only way to measure things there is neutrino oscillations. And therefore, our next subject, with which we will start tomorrow, is neutrino oscillations, which is an attempt to measure simultaneously the masses and the angles. Thank you.